So just kind of a brief recap. Uh, so this is the fourth webinar that we have in the series. So the first three webinars, well, the first one was overview of simulation and CPG, followed by rigid packaging simulation, and followed by the flexible packaging simulation. So in this case, we look specifically at the transportation scenario for consumer goods. I will just very briefly introduce. I just want to briefly introduce the company Vias. So we are a solution partner of Dassault Systems Simulia, and we have deep expertise in the Simulia suite of products: Abacus, Eyesight, EFISAFE, Tosca, CATIA, Delmia. Also, our team consists of PhDs and masters typically, and many of us are ex-employees of Simulia. We also have a great deal of experience in the different in the different industry verticals, from consumer goods to oil and gas, machinery and equipment. And if you need any help regarding any of your simulation needs, please feel free to shoot us an email, or if you need more information, please feel free to contact us. So with this, I will hand it over to Jose for the first part of the simulation on the model preparation, and uh, and I'll take up on the simulation part later. Jose, can you take on
Yes,
the
of course.
model preparation part?
Can you hear me?
Yes, we can hear you. Yeah, so I'll let you drive.
Thank you very much. Hello, everyone. So yes, I am. My name is Jose. I am a business consultant in the consumer packaged good and retail industry, and I am pleased to introduce to you the packaging solution that we have developed for this purpose. Uh, so uh, I'm trying to have the control of the slide. I would like to move forward. Okay, yeah. So it works. There was some delays. Sorry for that. So what we are going to cover today is a holistic way to go from package design to simulation. And we are doing that using the 3D experience platform, uh, which give the advantage of having a seamless digital continuity between all the tasks. And of course, the advantage of this digital continuity is to drastically uh, increase the speed and reduce the time to market, which is a common objective in this industry. So we are going to go and to review into details the different process elements we have here. And I am going to start with the creation of the package using a dedicated application of CATIA, which is called CATIA Structural Package Design. So the in few words, the advantage of this design solution, design application, is first of all to be a 3D native application. So it means that you are going to be able to design here, for instance, the the secondary packaging around the bottle, around the primary packaging. So what it brings, in fact, it helps to enhance the collaboration between the different stakeholders of the project. And for instance, here, a brand manufacturer with the packaging supplier dedicated to carton packaging. So it enhances the collaboration and it guarantees a strong brand image all along the design of the different component of the packaging system. From here, you can manage all the folding, all the different folding that you are going to create. it can be cutouts, perforation, crease, everything can be defined using this application. And from there, once you have defined your package, you can also map the artwork in order to have in in a few steps a global view of the final packaging with the shape and its artwork. And of course, you can then export the model into a DXF format in order to prepare the converting task, which is the number 6 of the slide that you have here. So to give you a better understanding, I just want to show you a short video to let you understand how we can make such a package. So first of all, we start with defining the characteristic of the carton that we are going to use. And from there, we start the creation. So first of all, as I said, we start by creating around the primary packaging. We are going to define the different characteristic of this packaging, the cutouts, uh, all the all the elements, including the lockers to create the package. And to make such a packaging, you have also to manage the sequence of the folding. It is very important. So this is something that we are able to do. And finally, we are ready with a DXF file ready to be sent to the converting. And we have instantly always the capability to go from a 3D view to a 2D view. And finally, as I said, you can have for the validation, for the marketing validation, you can have a realistic rendering of your packaging. So everything is already virtual, but we have the capability to prepare all the work through this application. Once you have defined the consumer unit, you are going to work on the tertiary packaging. And here I want to focus on the capability that we have to use and to design using templates. So working by reusing existing parts, existing templates, instead of starting from zero, of course, is a great advantage when you want to reduce the time to market. And you have at your disposal in the application the templates coming from the two major catalogs, the FEFCO and the ECMA catalogs, so that you have with you a large bunch of templates, box templates available. So again, I have here another video to show you how you can easily work by what we call parametric design to create a new box using an existing template. Here, a packaging coming from the FEFCO catalog, and how you can adapt this this template to your specific needs by having the capability to define the number of bottles, the number of packs that you want to have in this transportation box. So this is what we show here. We have here a 2-pack box, and we are going to show you how we can, just by changing some parameters, extend the size of the box in order to have more bottles into the transportation box. So you can see how agile is the way of working using parametric design. And you can also make some refinement, some holes to create handles or to let the label visible. Uh, Everything can be very quickly. But of course, when you are doing that, for instance, if you are making holes to create handles, you are going to modify the structure of the box. So that's why the simulation is going to be very important to make some validation, for instance, some compression test. And for that, we need to go easily from the design model to a model which is ready for the simulation. And for that, we have implemented an easy path to transform the design model into a model which is enabled for simulation with SIMULIA, that, so that we can transform a solid model into a surface model and having something which is ready to be used for simulation. This is what we show you here. We show you there how you can easily prepare a model to be ready for the simulation. So everything here is done within a single application of CATIA. And then you enter into the SIMULIA environment in order to make the right meshing that is going to be required for the simulation. So this is an illustration of the seamless continuity that we have between design and simulation. And the next step is to prepare your package for transportation. So we are going to see here how you can easily create a model of a palletization. And we are going to introduce some optimization routine which are available along our application. Here, just a short video to introduce the topic. So we are going to show you different way of using optimization routines. Here, what we want to do is to optimize the number of bottles that you can have in a defined box, and by adjusting different options, you can see that you can improve the number of bottles which can enter into such a box. So this optimization routine can be applied to optimize the filling of a box, but it can also be extended to optimize the way you are going to stack boxes on a pallet, So this is here an example of how you can optimize a pallet by giving some parameters like the height, like the weight, and you can see that automatically uh, we are going to optimize the stacking of the box to increase the number of boxes that we can carry, but also how we can manage them to increase the stability. That's why you can see that we have different way of stacking the box. And after again, you are able to prepare the pallet model in order to make some simulation, and Swapan, you are going to give more insight on the way of working on the simulation. This is just a short overview of all the simulation you can do relating to palletization and uh, and transportation. So here you can capture all the forces which are applying during a braking by having sensors on a real truck. And once you have captured these forces, you can apply them to the pallet and check how the pallet is going to behave and validate that it is keep it will keep stable. This is what we explain here, and Swapan, you will go into more details. And for instance, so sometimes the forces are too strong. Okay, so I think that just to summarize the capability of the pallet optimization that we can provide, you have here some example of how you can arrange the block on a pallet to optimize either the number of blocks and also the stability of the pallet. Different way of centering the blocks. It's really important for the stability here. It's what we have, and now we have designed a holistic packaging system from primary to secondary to transportation to pallet, and all these elements are available for simulation. And this is the next step that we are going to see with you, Swapan, and I give you back the control.
Thanks, Jose. So I'll continue the part on the simulation. So again, to kind of re-emphasize, so this is one kind of holistic platform, the 3D experience platform, where you can create your model, and where you can create your model, you can also simulate it, you can integrate it with your manufacturing, and also and also your requirements and stuff. So the advantage so the advantage is that you do not end up transferring data from one platform to the other platform, or all the friction associated when transferring data from CAD to FEA. None of this is existing. So on the simulation part, we have two things to cover. One is the packaging static simulation and the transport dynamic simulation. So I'll take some liberty to go into the transport dynamic simulation first, and then revert back to the packaging static simulation, because some of the material in the packaging static simulation we already covered in webinar number 3. But I do want to again touch back on it as we go along. So before we jump into that, just kind of a brief overview of the SIMULIA brand of Dassault Systems. So under the SIMULIA brand, we have various products which are geared for the simulation technology. So we have the multi-physics simulation, which is our flagship abacus solver, and it is extremely strong for highly non-linear analysis, structural analysis. I would say probably I would say probably the strongest in the world right now as far as nonlinear structural analysis goes. We have Abacus for the multiphysics. Then we have eyesight for optimization and workflow automation. We have Tosca for non-parametric optimization. If you want to optimize your material usage in a non-parametric fashion, we can use Tosca. We have FE Safe to determine the life of the product. If you need more information on any of us, we would be more than happy to help you out. Just shoot us an email and we'll be willing to help. All right, so jumping straight into the transportation part. So if you really think of the transportation, well, I mean, the integration of the transportation and simulation, what do you really need to know? We need to understand what are the normal forces on the pallet during its entire transportation journey, and like what are the different forces on it. One would be the normal forces, which would be governed by the kind of terrain you encounter. So you can bring in your different terrain possibilities, I mean, what are the likelihoods of hitting a bump and all of those things. And if we have those inputs and we apply them inputs onto the Pele, we can get a prediction of what are the acceleration and forces that each of the individual boxes is likely to experience. Then we have the acceleration and the deceleration forces. Acceleration, when you accelerate, what is a what is the force in the sideways direction, and when you brake, what is the force it encounters, and when you take a turn, what are the lateral forces that we need. So as we have seen, we define the model in CATIA. We can basically integrate the CATIA and the SIMULIA pieces here. We can get the loads from the CATIA systems application where you've defined it, and then we can do a much more exhaustive analysis where we can get an idea of the normal forces uh, on the pallet. And we will look into a few animations here. We already did look into some part of it. So here, this we can get a sense of what are the normal forces, and we can export that forces to a CSV file for further analysis. So we can copy the CSV file for further analysis, and when we can do much more detailed analysis on each one of them. So on a similar way, we can do that for acceleration and braking. You can see how the forces vary, as we do the acceleration and braking, and we can export those values when we do the when we do either the acceleration or braking, and do a much more detailed analysis subsequently on the individual pallets. So we export this again to the CSV file. So similarly, we can do that for for the cornering simulation. When you take a turn, what are the lateral forces that it is likely to encounter, the lateral acceleration on the pallets. And so I would not go into the simulation part. I mean, I wouldn't go into the animation of that. We would look further detail. So I mean, like once you have the forces, you're actually ready to do much more work with it. But before we jump into that, say you have your pallet, you want to wrap the pallet. You want to understand what is the wrapping strength. You want to understand what is the height. You want to understand what is the contact pressure. Now, since you have the normal forces, the forces that it is likely to encounter in its transportation journey, you can use that as an input to understand things at in a much better level uh, at this point. So, so what we can do is a wrapping simulation to understand the forces. I mean, so here you see the wrapping simulation. We wrap the paper uh, along the pallet. We can look at the contact forces. We can look at the stresses. We can optimize the height. We can optimize the thickness of the material. I would get into the details of the paper modeling because it's kind of a tough simulation. How do you actually model the shrink wrap? How do you model the wrap? And that's kind of, I mean, one of the strengths of solvers, that it can really handle this kind of complex contact and nonlinear analysis. So you can do much more exhaustive studies on an individual basis. And next, I mean, we can basically, as I said, we have the normal forces from the transportation journey. We can basically understand the strength of the wrap here. So in this case, you can see exactly, we'll look more into that. So you have your wrap study here. You're looking at when you apply the normal forces, what would be the expected stresses, the contact pressures, and those details. We can look into those things. So we can look at it, and we can there are a number of things we can do on the post processing side uh, to uh, to kind of understand in a much more granular way what would be the impact of the forces. So yeah, we are importing the accelerations we had from the previous one into this model, and we are going to do further simulation on this. So we know that, okay, you know this is like, okay, well, I mean, if we don't have a wrap, what happens? And if we don't have a wrap, we know what happens. So then the next step is logically, okay, then let me put in a wrap. Let me try to vary my thickness of the wrap. Let me try to experiment with various heights, and let me see if that makes a difference. uh, we can also do many other types of tests. I mean, there's a cool kind of thing. We can do a zipper test. We need to be able to model failure for this kind of material, and the solver has a number of capabilities to be able to do that. There are a number of approaches we can take, right from the details of fracture mechanics to more simplistic approaches. If you have the test data, we can go into this. So we can also do handling tests. So we can see this. I mean, this was the model created in the earlier part, and you know we can do, actually, we can see the power of visualization here. We can actually see the impact of, I mean, as we do the handling, how the bottles interact among itself. The contact between each of the individual bottles is captured, and we can see, I mean, if necessary, we can revert back to optimization. And I mean, optimization when we and we can see if it would make a difference if we can pack in more bottles or we can pack in less bottles. And all right, so I mean, we can do drop testing. I mean, that is pretty standard. But the cool thing here is that we have a wine bottle with a packaging, and we do the drop test with that, and we see that, okay, if this is breaking, should we add more reinforced materials or not? So here we do it without any reinforced material. I mean, and we see that, okay, it's likely to break at the bottom at this velocity. So how do we avoid that? And we can avoid it. So in the next step we'll see how we can avoid it. We add some support here, and we do the simulation and see if this would help. And we can we can optimize the amount of material required in the support. Make sure that uh, we are not over designing, or it's not under designed. So so you can see the power of the simulation. So now again, remember that this is all integrated with the model creation on a single platform. And typically, I mean, and to me, that is kind of a game changer. I've been in this industry for about a decade and a half, and there is a significant amount of overhead involved in transferring data from a CAD package back to your simulation, and uh, and that to and forth usually isn't frictionless. So having looked at this, let's look into some much more details of the people modeling here. So what are the for the details of people modeling, what are the different challenges that we really have? Now, to actually simulate paper is much more difficult than to simulate aluminum or steel, because paper does not follow the usual laws of continuum mechanics. So I mean, for with steel and aluminum, you can define your linear elasticity, it is isotropic, and you define your plasticity. The mathematical modeling of those metals is much more simpler. Where in the case of thin, or in the case of packaging material, yeah, really some of the laws, I mean, like if the in plane tension, if you're expecting a particular bending stiffness with your in plane tension, you may not get the exact value. Your bending stiffness is dependent on a number of factors. So we need that framework which can model those all this complexity along with failure and so forth. So really the end goal is that we need to produce a product that has high bending stiffness with as few fibers as possible, and then understand that how would that product behave under your various loading scenarios for box compression testing, for sag, creep, etc. So again, just to kind of get a little bit into the details here. So if you have your cardboard material, if I look at the cross section here, if I look at the first plot here, if I apply my bending, if I apply a force, my bending stiffness initially is going to be proportional to the force I apply. Now, as I keep applying more and more force, I'm going to see more and more failures in between the plies. I'm going to see some delamination happening in the plies. And as I see more and more delamination, it's going to buckle. And at some point, it's not going to matter. The bending stiffness is going to be constant. It's just going to buckle straight away. I mean, basically, it's just going to go down straight away. So we need to be able to capture all this details in the simulation. And so this actually is really the hard part. Though from a simulation standpoint, if you look at those animations, the earlier simulations look kind of cool. But to get this right, you need a solver which is basically powerful and capable enough to handle this. So this this is a simulation I had worked on the creasing of paper, and we had to write our own custom material model at that point to be able to get this right. So we what we need really, in a nutshell, I mean, and this I'm giving kind of a simplistic overview. We need elasticity, and elasticity is likely to be different in every direction because the paper material has more fibers aligned in the machine direction. So the stiffness in that direction is different than the stiffness in other direction. So we need a framework to be able to specify that. Orthotropic elasticity, we need plasticity, so we have your elastic zone, we have a plastic zone. So in the plastic zone, once you apply, it doesn't recover, the stress doesn't recover, the deformation doesn't recover completely. And then you need a framework to be able to model failure, and you can define all of these. So we have number of material models to be able to do it. And when you're doing modeling at the I mean, we can then investigate, once we have the material model defined, we can investigate what would be the impact on on the different corrugation layers, and we can try to optimize this for the different corrugation, uh, whether we need a single corrugation, whether we need a single corrugation, or whether uh, should we have multiple corrugations. We can do your compression testing, you can do your bending testing to understand those details here. So once you understand what kind of material you need, I mean, for the corrugation, I mean, you can kind of homogenize it and put it back in our earlier models. I mean, so you can actually get rid of the corrugation and try to capture the material properties of the corrugation at a much more macro level, and then apply it to the model which we had created earlier here. So here we are going to create an explicit dynamic step. So it's a nonlinear material. We are expecting a high deformation, and the explicit solver is best geared to handle that. So we can define contact pretty easily. There is a capability called general contact in Abacus. So what it does is that you don't need to define all the contact interactions individually. You can define it at a global level, and the solver will automatically take care of it. So we can apply it either a load, or we can apply displacements. We can treat the plates as rigid body, and we can uh, we can and so the upper and the lower plates here are treated as rigids, and we're going to apply some amplitude here to see how the box deforms. We can monitor the output and output variables, the displacement, the forces. Next, we do the simulation checks. So you can look at the sag. So if you want to keep all the details of all the corrugations in this model, it is definitely possible to take that approach too. Or you can prefer a much more macro approach where you, once you understand the material properties from the corrugation, you apply it on a macro scale here, so to simplify the model. So you can look at the sag, and that gives you an indication of how much is the sag in the box. So we move on, so we have various history plots, we can get the reaction force and all those details. So we can understand if this will be able to be, it will be compliant. I mean, how much is the force, how much is the maximum force it can take, and we do have an understanding of what is the maximum possible force it's likely to encounter from uh, from the transport simulation we did earlier. So we can also, I think the coolest thing is that we can really try out all the design modifications required, yeah, to see. I mean, okay, I mean, can we change the design a little bit? Can we alter it? What would be the impact? Can we save on some material? If it's under designed, if it's over designed, we can do those things. And you can create parameters at the CAD level, and those parameters will be respected at the simulation level. So here we create these two holes, and we can do those simple we can do those changes, and we can try and we can explore the design space much more exhaustively. So the same thing with physical testing, it's going to cost you a lot of money, but I mean, so this, if you have confidence in your model, and if a powerful simulation, it's a very powerful technique which can help eliminate a lot of cost. All right, so I move on further in the interest of time. So we have, once you do that, you can do your, at this level, at the individual box level, you can still do your vibration testing. We have the data about what is the forces we're likely to encounter, on the what are the normal forces or the lateral forces each box is likely to encounter in its journey, and then you can do that at the individual level. So I'll not go into the video here again. So it'll be a repeat of the earlier video. And just kind of a reiteration. So I mean, this is a single corrugation we had. So you can actually optimize for the number of corrugations, whether you need one layer, two layers, and you can check on whether you have optimized for that. If you need more strength, you can try those things out. Okay, this is what I get with one layer. This is what the stress looks like with one layer, and this is what it looks like. So this, we can see, is much more stiffer, and depending on what is the expected load in service, we can optimize for that. And once you have the data from here, you can, once you know the stiffness here, you can approximate the properties of the corrugated cardboard and do more work over there. So this is an example of a real life simulation which was done. So what we have is simulation of box compression test of washing powder packaging. So on the top is the real picture, and you can see it's okay, it's stressed in the corners. You can mimic the simulation here. And so just as a recap, we can capture wrinkling in the paper material, and even for the manufacturing. So here I haven't gone into the details of manufacturing of paper, but even that simulation we can handle. So, and that that has its own different set of challenges, uh, but we have the framework and the physics to be able to manage that, to be able to handle that. So you see here the distortion of paper as it moves to the manufacturing line. You can have a much more simplistic 2D model, just to understand, just to give a better idea of the contact pressures in the rollers, and all the papers, and you can do it in many ways. So finally, I mean, this one slide just to recap everything what we have. I mean, what we covered here, and from handling drop and impact, transportation, vibration, stacking, uh, and so I think we are out of time. So I mean, and this is likely the end of this presentation. So if you have any questions, please feel free to shoot us an email at support@viascorp.com. If you have any questions now, we'll hang on for a minute. If not, we will end the presentation here.